All right, STEM class. So you're going to have a slow car, okay? And you're going to have to pit it against another slow car, move them at each other, and you're going to have to predict when and where, after how much time, and where in between they're going to meet. So, in order to do that, you need to know systems of linear equations, or at least how to apply them in physics, and that's what we're going to go through here today. So first of all, you probably already did something with this, but I'm going to show quickly how to do just the basic math of linear systems. And then we're going to look at the graphing of the math and then actually apply that math. Math. So math is just the solving of the system where you get an x and a y coordinate. You get a number for x and you get a number for y. There's no context there, right? Now, if you graph it using the slope-intercept form of these types of equations, you actually get a little bit of context. You get a little graphical representation. But it's not until you actually apply the math and do physics, applied math, and it works with speed, that's when you finally actually get a better idea of what's going on. So let's just talk about strictly the math, okay? Now, if you're going to solve an equation or a system like this, y equals 2x plus 1 and y equals negative 3x plus 5, well, you go ahead and you set them equal to each other. So you say 2x plus 1 equals negative 3x plus 5. Nice and easy there. But now you've got these x's on both sides and numbers on both sides. So you have to simplify it. So let's see, I want to, you know what, I'm going to add 3x to both sides. Okay. And that gets me left with 5x plus 1 equals 5. Alright, that's a good start. But let's see, we still need to get rid of this 1 here. So I'm going to subtract 1 from both sides. And so what I'm left with is 5x equals 4. And then I'm going to, since x is multiplied by 5, I'm going to divide both sides by 5. And that gives me x equals 0.8. Alright? But that's not it. We have to get an ordered pair. Right now, we have 0.8. Ooh, haven't done this in a while. My handwriting's terrible. So what we do then is we plug it into one of these original equations. We take this x and plug it in. So let's do y equals 2 times 0.8 plus 1. And so 2 times 0.8 is 1.6. Add 1, that equals 2.6. So y is 2.6. And therefore, we can add that up here as our y coordinate, and we have solved the problem. Alright, but let's say we were graphing something like this. You know, with y equals mx plus b, that m is the slope and b is the y-intercept. Okay? So, if we were to graph one of them, let's say we graph this one first. Y equals 2x plus 1. 1 is your y-intercept, so you can already go over here and plot 0, 1 as your first point. Now you also know that the slope is 2, which, if you remember, slope is the change in y over change in x. So if the slope is 2, that's the same as 2 over 1. That means the y increases by 2 for every increase in 1 on the x. So if I increase 1 in x, I have to go up 2, right? So my y went up to 3, and my x went up to 1. So then I got to go up 2 and over 1 again, and up 2 and over 1 again. And so what you end up getting is this nice line, right? Alright, so let's graph the other one. Let's graph this other line. Y equals negative 3x plus 5. We have 5 as the y-intercept, and the slope is negative 3. So we're going to go down 3 for every 1 we go over. And down 3, oh, we got to go negative here. That's okay. We'll just put it there and draw that line. Alright, so now, the whole point here is that, well, let's see. There appears to be a little spot here where the lines intersect, and I bet you we could estimate what that is. Let's see. Ooh, that looks to be about, I'd say, 0.8. And I'd say like 2.6 or so. Oh, wow. Look at that. That's exactly the same as the solution before. So really all you're doing when you're graphing these, or when you're solving these in y equals mx plus b, is you're finding, all you're really doing is finding this intersection, okay? And that's why, let me get that out of there, when solving a system of equations, you are finding their intersection. That's the big point. So now lastly, okay, what we've got here is the physics. Let's apply this to a real situation, okay? So let's say you had, I don't know, let's say you had a track here, and let's say it was about, let's say, 7 meters long, okay? So 1, 2, 3, 4, 5, and 6, right? And so let's say you start a car, let's call it the red car. Let's say you start this red car right, and you know it's a car because it's round. Oh, I'm just terrible, okay? So you start this car right here at 1 meter from 0, okay? And you also have another car over here, and let's say you started at 5, okay? Now, this car is actually going in the opposite direction. This red car is going in that direction. And what you notice, let's say you actually let them go. They move at a nice constant velocity, like a slow car. And let's say it moves over so that it covers 2 meters in a second. So after 1 second, it's here at 3 meters. Then after another second, well, it's over here. So after 2 seconds, it's at 5. And then after 3 seconds, it's over here at 7 meters. So it's moving across the way there. And then the blue one, let's say it's going the opposite direction. After 1 second, oh my gosh, it's all the way over here after 1 second. And it's probably way over here after 2 seconds. Okay? It's moving a bit faster, right? So how could you actually show this a little more graphically and understandably? Well, that's where a graph comes in. So if you go back, if you start thinking about this red one here, okay, this red one, it starts at 1 meter down the track. Another second later, it's 3 meters down the track. And then 2 seconds in, it's at 5 meters down the track. And 3 seconds in, it's 7 meters down the track. So you get this nice line that I could draw if I actually had good handwriting on this bamboo pad thing. And then you go back to the blue one, and it starts 5 meters away, see? And after 1 second, it's at 2 meters from the beginning. And it actually gets close to -1 there. And so you get this nice line there. Holy moly, are you seeing something there? You are. You're seeing a connection to the one before because the previous graph was exactly the same graph. Here's the only thing that I did, okay? All I did was I took these equations and applied them to a physical situation, okay? When you're talking about distance, speed, time, that sort of thing, y equals mx plus b is different. Here's what I did. First of all, I defined y as being distance in meters, okay? That's all I did right over here. I said y-axis is distance in meters. And I said x, that's going to be time, and I'm going to measure that in seconds. Okay? So, x is 1 is 1 second. 2 is 2 seconds. Okay? And then what I did, the way this works, remember that m is slope, right? Now, if m is slope, that means it's the change in y over the change in x. Now, what did we just define y as? Distance. What did we just define x as? Time. So, do you recognize distance over time? That is speed or velocity. And we're going to use velocity here. So really, you get that m, the slope, is the velocity of whatever you are measuring here. Now, that only leaves us with b, the y-intercept. Well, the y-intercept here is at time 0. Where is it? Well, that's the starting point. Okay? So, really, all we've done is we've transferred this math to a real situation. We said that the y is the distance, the x is the time, the slope ends up being the speed of the car or whatever it is, and b is just that starting point. And so what we can then do as well is we can just get rid of all this extra mumbo jumbo that's in gray here and just say y, that's distance, we'll call that d, equals m, we said that's the slope, we said that's the velocity, we'll call that v. X we said is time. Let's call that t. And then this starting point, that's also a distance, but we're going to call that d sub I, or subtext I. This right here, folks, is how you find the distance, or where something is, based on its initial position and how fast it's going and how long it's been doing that. That's the speed equation. That's the velocity equation in physics. Essentially, what we just did is we said, okay, we know how the math goes. Okay? We know how the math goes. You can just sort of solve and get this. You can graph it. That point, 0.8 and 2.6 is the intersection. And when you actually apply the math, you can figure out that these two cars are actually going to meet at 0.8 seconds and 2.8 and 2.6 meters. We found out by setting them up like this, we were basically asking the question, where / when do they meet? That's it. That's all we were doing. And we found out that since x is 0.8, the time is 0.8 seconds, and the position was 2.6 meters. So now you can determine, if you know the speed of a car and where it starts, and the speed of another car and where it starts, you can find out exactly where they meet. You know where to set up a camera to watch them crash, and you can do a whole lot more physics and a whole lot more fun, right?